Today's speaker is Dr. Lauren Weiss. She is an assistant professor in the Department of Physics and Astronomy and is a member of the Astrophysics Group. She uses observational techniques to discover planets around other stars, and these are called exoplanets. Exoplanet science has led to the discovery of more than 6,000 planets orbiting other stars, which is just, it blows me away. That's more than I would ever have expected. And researchers use both ground-based telescopes and the NASA Kepler and TESS space telescopes. Before being hired at Notre Dame in 2021, Dr. Weiss was the Beatrice Watson Parent Postdoctoral Scholar at the University of Hawaii at Manoa, Honolulu. She earned her doctoral degree from the University of California at Berkeley, her master's in astronomy from the University of Cambridge, and her bachelor's degree from Harvard. Please join me in welcoming Dr. Lauren Weiss.
Hi, thank you. Thank you so much for joining me. It's a beautiful sunny day on our planet Earth outside, but we're here indoors so that I can tell you a bit about what my group at Notre Dame is doing toward finding what we hope will be Earth 2.0, a world something like ours.
At our hearts, we are seekers, observing stars and searching distant skies, looking for something familiar. And 3 decades ago, a remarkable signal cut through the cosmic dark. The discovery of the first planet beyond our solar system orbiting a star like our own. And soon, there was not just one discovery, but thousands. As our curiosity for what is out there has grown, so has our science. We are discovering a greater diversity of exoplanets than ever before. Some ablaze, others frozen solid. A few changing the way we see our own solar system. But there's one we haven't found. A planet just like ours. At least, not yet. Is Earth the only home for life? Or are there other habitable worlds waiting to be found? With every planet we discover, we get closer to answering that question. We're entering the next great chapter of exploration, discovering worlds beyond our imagination, to look for planets that could support life, to find our cosmic neighbors, and to remind us that the universe still holds worlds waiting to be found.
So we just heard that over 6,000 planets have been discovered around other stars. That number of exoplanets just topped 6,000 this week. Really, what I want you to take away from this is we're not just finding 1 or 2 or 3 exoplanets, but thousands of them. Enough to do statistics and make discoveries about what kind of planets are common and whether our own solar system and the Earth is common or rare. So how did we find 6,000 exoplanets? This is a beautiful view of the night sky over the Toadstool Formation in Arizona. And as you can see, the stars are quite beautiful, but it's not obvious upon looking at them which of these might have worlds like our own. So I'd like to show you a very special planet. I've circled it on this photograph. Does anyone know what this planet is? Earth, that's correct. This is Earth as viewed from the NASA Voyager mission in 1990. The great scientist Carl Sagan said, let's turn this space probe, which at the time was flying out of our solar system. It was at the orbit of Neptune. He said, let's turn this thing around and take a selfie, a very long-armed selfie. And this is what we got. So he likened Earth to a mote of dust suspended in a sunbeam. The reason I show you this is to illustrate how hard it is to see worlds. In this case, using a telescope in our own solar system, that's what Earth looks like. The challenge of using telescopes to see planets around other stars, which are much, much, much farther away from our sun than the Voyager spacecraft was when it took this photograph, is what drives the research I do. So one method that we use for discovering planets around other stars is based on this. Does anyone know what this is? The sun. Good, that's correct. What else is happening here? A transit. Did anyone see this actual event? Maybe. This was the transit of Venus in 2012. A couple times per century, our planet Venus lines up between the sun and the Earth in such a way that we can see its shadow as it marches across the sun. So what happens here is Venus is blocking a small amount of sunlight. Now, when it comes to other stars, we can use this effect as well. If a planet has a configuration in its orbit where it crosses between its star and our telescope, what we can see is a change in brightness of the star. The star will maintain a steady brightness until that planet crosses in front of it, casting a shadow. We see a slight dip in the starlight, and when the planet is done transiting the star, the brightness of the star returns to normal. The light that is blocked during the transit is the cross-sectional area of the planet. And so from the amount of light that's blocked, we can figure out the size of the planet. Also, because planets have orbits which repeat, this transit-like event will repeat multiple times. And the time between consecutive transits is the planet's orbital period. So a little over a decade ago, a very great space telescope called the NASA Kepler mission was designed to study the statistics of exoplanets using this method. And it was designed in a way where it was capable of finding Earth-sized planets in Earth-like orbits. What you are seeing here is an artist's oil painting representation of the Kepler Space Telescope surrounded with a background of beautifully imagined stars and planets representative of some of the discoveries that Kepler made. Quantitatively, what Kepler found looks more like this. Kepler discovered that small planets are abundant. Every single gray dot here corresponds to an exoplanet discovered by the NASA Kepler mission. This is a graph with two axes. The vertical axis is telling you the size of the planet relative to Earth, with a few guidelines. Jupiter near the top, Neptune in the middle, and Earth is the bottom of those horizontal lines. You can also see the orbital period of the planet in days. And looking at this graph, I can tell that small planets are abundant. Look at how many of those dots there are smaller than Neptune. In fact, many as small as Earth, or even smaller. How many of these worlds might be capable of sustaining life? So if we really focus on the worlds that have similar sizes and orbits to the Earth, they might reside in, say, this pink box. And you can see that while the Kepler mission discovered quite a few planets in the top left corner of that box, it didn't discover as many in the bottom right corner. That's not because they aren't there. That's because the smaller a planet is, and the longer its orbital period, the harder to detect it is with the transit method. So this is a type of detection bias. One of my colleagues was part of a study to correct for this detection bias. And after making this correction, they found that 1 in 5 sun-like stars has an Earth-sized planet in an Earth-like orbit. So this is a very similar plot. The red dots now are based on a carefully curated sample from their bias-corrected study. And they're also looking at the orbits in terms of the amount of light that the planet is receiving from the star, which might be indicative of the planet's surface temperature and whether it could sustain liquid water. So this is really a remarkable number, I think. 1 in 5 Sun-like stars has an Earth-sized planet in an orbit where it might sustain liquid water. So if we extrapolate that number, or rather use that number for statistics, we arrive at the result that there are 17 billion Earth-like planets in our galaxy. And that's a staggering number. So unfortunately, Kepler was a statistical mission. It was really just designed to get these numbers. What it did not do was find the nearest Earth-like planets. So we are still a bit in the dark about where are the nearest Earth-like planets. Where should we look to find them? And once we find them, of course, we want to know, do they have life? All right, so what we've just heard is a beautiful promotional video for NASA's next big goal, which is to build a bigger and better space telescope than we've ever built, called the Habitable Worlds Observatory. NASA is still in the process of designing this telescope and figuring out, based on the design specs, exactly what we'll be able to accomplish with it. But these are the goals, is to be able to directly look at light from Earth-like planets and identify water and other signs of life. Now, this is enormously challenging if we think about that image I just showed you of our pale blue dot of Earth suspended in the sunbeam. It is so hard to directly image a planet. So the research I'm doing here at Notre Dame is aimed at accelerating our search for habitable worlds. So what we're doing is using the W.M. Keck Observatory to discover some of the nearest habitable worlds in preparation for NASA's big space telescope. We'd like to be able to tell this telescope where to point in order to potentially see these signs of life. So the way we are doing that is with a telescope that already exists right here on our own planet Earth. What I'm showing you now is my favorite mountain on Earth. This is Mauna Kea, a shield volcano in Hawaii. This is the big island of Hawaii. From base to summit, it's taller than Mount Everest. Its base is at the bottom of the Pacific Ocean. This is a satellite image. And if we zoom in, we can see a ring of white dots. Now, those are not geological features. Those are human-made. Those are telescopes, including the W.M. Keck Observatory, in which Notre Dame is a minor partner. So I use one of these telescopes to discover planets around other stars. And the way I do that is with what we call the Doppler method, which is illustrated in this animation. As a planet orbits its star, the planet is also pulling on the star gravitationally. And so the star wobbles in a reflex motion as a result of the planet orbiting it. As the star orbits the center of mass of the system, it moves toward and away from us. And in doing so, systematically compresses and stretches the waves of light that arrive at us. This is a consequence of the Doppler effect. So by looking for the stellar wobble, by looking for these changes in light, we are discovering other worlds. Specifically, what happens is we can see how long it takes the star to make an orbital cycle. This is the orbital period of the planet. We can also measure the amplitude of the star's oscillation, and from this we can derive a mass of the planet. So this technique has been really wonderful for finding exoplanets. In fact, the very first exoplanet discovery nearly 30 years ago was done with this method. This particular discovery was of a Jupiter-mass planet orbiting its star in just 4 days. We call it a hot Jupiter. So the Nobel Prize was awarded for this discovery just a few years ago, and in a couple weeks, I'm going to the observatory in France where this discovery was made for a 30th birthday celebration in honor of this planet. All right, so we're trying to answer the question, where are the nearest habitable worlds? And my group is using this Keck Observatory and the Doppler method to find these planets. But in the remaining time, what I want to share with you is how we are leveraging some observed patterns among the exoplanets to refine our search. Yes, we are searching broadly, but the more we can refine our search in advance and be strategic about which stars to search for habitable worlds, the more likely we are to have success. So a lot of my research has been dedicated to searching for signposts that would help us find the next Earth. These signposts include a distinction between rocky planets, which are good for life as we know it, and planets with gas-rich envelopes. We've also discovered a pattern in the sizes and the orbits of planets. And just recently, my group also discovered a pattern linking the Jupiter-like planets to small planets in planetary systems. So I'm going to briefly show you those patterns. I won't have time to delve into a lot of detail, but you can certainly ask me more questions about them after the talk. So let's start with the rocky and gas-rich exoplanets. So a lot of those planets that were discovered by Kepler have sizes intermediate between the Earth and Neptune. As we know, Earth is great for life. We're all here and living, I hope. Whereas Neptune is not really conducive to life. So some things that contribute to life are a rocky surface. This is needed chemically for chemistry reactions to occur efficiently on a two-dimensional surface. And liquid water, which also is water is a universal solvent. That's really critical to the chemistry of life. So fortunately, we can measure which exoplanets have rocky surfaces, and that's the work I'm about to share with you. We cannot yet measure which planets have liquid water on their surfaces. Hopefully with the Habitable Worlds Observatory that might become accessible to us, but we're not there yet. So let me tell you how we found the rocky surfaces. So this relied on combining the two methods I shared with you. First, we discovered planets with the transit method, from which we got the sizes of the planets. Then we followed them up. We continued to observe them with the Doppler method in order to determine planet masses. By combining these, we were able to calculate the planet's bulk densities. And as you might realize, something that's rocky is denser than something that's made of gas. And so once you know the mass and the density of a planet, you can infer its composition. So I'm going to walk you through a few plots quickly. These are the bulk densities of all the planets we knew about in 1990. So this was the year of that beautiful pale blue dot image. At this time, the only known planets were those in the solar system. This is a graph with axes that are showing you the planet's bulk density on the vertical axis and the size of the planet on the horizontal axis. And you can see our solar system planets and their positions on this plot. Our terrestrial planets are on the left. They're small and high density. And then our ice giants, Uranus and Neptune, are lower density and larger. Here are the exoplanets that we've discovered. I've had to shrink the solar system planets to little squares so you can see all these exoplanets. So we've discovered thousands of exoplanets, and we've also been able to measure the masses of hundreds of them, contributing to the data that you see here. My colleague and I noticed a couple of patterns in this data set. What we noticed was that small planets seem to rise in density as they get larger, but then this pattern turns over and the density falls with increasing radius. We interpret this as a transition between the rocky planets that might be good for life and those with gaseous envelopes. So the rocky planets are on the left side of this diagram, and the gas-enveloped are on the right. The consequence of this is that if we think about sort of a family tree of exoplanets, including giant planets like Jupiter and planets like Neptune, we now have a better understanding of which planets might be rocky like the Earth. They're the ones that are smaller than this transition we found at about 1.5 times the size of Earth. Another pattern that we discovered links the sizes of planets and their orbital properties. So I'm not the first person to look for patterns in the solar system. Johannes Kepler, one of the great giants of solar system astronomy, looked for patterns in the planetary orbits. He tried to circumscribe them all with geometric solids, the Platonic solids. And he succeeded in this up to the orbit of Saturn or so, but then the pattern broke down for Uranus and Neptune. A bit later, two astronomers, Titius and Bode, found a very nice regular geometry in the orbits of the solar system planets that's often referred to as the Titius-Bode law. That law works pretty well, but it doesn't perfectly describe the planets. So that's the stage when I entered the picture. I was working with a team where we were characterizing the properties of 909 transiting planets in 355 multi-planet systems. So I used data from the Kepler Space Telescope to measure the sizes of these planets and their orbits. And with data from the Keck Observatory, we were able to reduce our errors in those measurements, which is really important. And in doing so, we produced the gallery that you see at the right, where each row here corresponds to a single planetary system. And the planets are organized with the star would be at the left, and their orbital distance increase going to the right. And each dot is scaled to the size of the planet radius. So I looked carefully at these data, and I noticed a couple of patterns, which were that planets in the same system often have similar sizes and regular orbital spacing, a bit like peas in a pod. So this was a really exciting discovery. Before I found this in our data, people thought that planet sizes and orbits were just kind of random. And now we know that there's this really marvelous order. This might be an example of something called a self-organized system, which is a really cool mathematical thing that can emerge. So we're still trying to understand what are the laws of physics that make planets in this really nice pattern. I don't have a definitive answer for you today. My colleagues who are theorists have come up with a bunch of ideas that we can test. And I'm going to share one of those with you now.
Scientists have a new theory to explain a strange consistency seen in planetary systems around other stars. Astronomers have found that many stars prefer their inner rocky planets to be all of similar sizes, but that size varies from system to system. This pattern can be explained if young stars develop narrow planet factory rings. Small objects in the ring would tend to clump together, forming a planet in a few million years. Gravitational interactions with the gas in the disk would shift the planet into an orbit closer to its star. This makes room for more planets to form one after another while the ring persists. The structure of a star's ring would determine the typical size of the planets in that system. Sparser rings would tend to form smaller worlds, while denser rings would make super-Earths. A ring should form just beyond the point where the star's heat vaporizes rocky materials. This theory is based on a similar concept proposed to explain the formation of the moons around outer planets in our own solar system.
I will finish up by telling you about one last pattern, which is a link between Jupiter-like planets and small planets. So this is work that I did here at Notre Dame with a wonderful, talented postdoctoral scholar, Dr. Matthias He, who now works at NASA. So we used a beautiful data set that I had spent a decade gathering to search for patterns between Jupiter-like planets and small transiting planets. And it was actually Matthias who found this pattern. So what you're looking at here is another gallery of planetary systems where each row is a system. The stars would be on the left, and the planet orbits increase going to the right. And there's also organization along the vertical axis. Near the top of this graph, the transiting planets have a lot of gaps in their spacing. Whereas near the bottom, the transiting planets have very regular spacing. They have no gaps in their spacing. And what Matthias found is that the Jupiter-like planets are prevalent among the systems that have the gaps in the spacings of their inner planets. So those red circles up there represent the Jupiter-like planets that my team had discovered with a decade of data from the Keck Observatory. So we now have this clue that Jupiter-like planets are actually playing a role in the formation and dynamics of small planets, possibly including planets like Earth. And of course, our own solar system has a Jupiter, which should be a big clue. Our solar system is up here in the middle with dots encircled by teal. All right, so in summary, what I've been telling you is how my group at Notre Dame has been accelerating our search for Earth 2.0 using the Keck Observatory. We are leading a large NASA program looking for Earth-like planets around the nearest stars in preparation for the Habitable Worlds Observatory mission that NASA hopes to launch in the next couple of decades. In the meantime, we are using signposts to refine and organize our search. And these signposts include a distinction between the rocky and the gas-rich exoplanets, a pattern among the sizes and orbits of planets, and also a pattern linking the Jupiter-like planets and small planets. Thank you so much for your attention, and I will take any questions.
For questions, I'll pass around the microphone. If you are able, it would be great if you could stand up when you ask your question, and that way we can get proper video. Who has a question?
So I had the fortune of attending both the 2017 and the 2024 solar eclipses that came through. And something interesting I noticed about the light being blocked from the sun by the moon was that it wasn't like a linear correlation to how much was being covered. Like when the sun was halfway covered, it was pretty much just as bright as a normal day. But when it got to like 80%, 90%, as it got closer to 100% covered, the light dropped really quickly. So when I was initially looking at this earlier, it looked like the light blocking was modeled linearly, but in the way that I sort of saw earlier, I was wondering if there's sort of more complexity to how you're able to create that model of generating sizes.
Yeah, what a great question. Thank you for that, Ignatius. Really, it's the human eye here that is either to blame or praise for that effect that you just described. Our eye perceives light logarithmically, much like our ears perceive sounds logarithmically. That's why we have the decibel scale for volume. And similarly with light, our eye isn't really that sensitive unless changes become very dramatic. So hopefully that answers your question.
It does, thank you. Never knew that.
Hi, my name is John, and I was going to ask about how you happen to catch these planets transiting. I mean, is it something you just point your telescope at a particular section and wait for it, or do you somehow predict it, or what happens there?
Fantastic question. Thank you, John. Right, so the question is sort of how do you know when the planets are going to transit? How do you catch them? And the way we did it with Kepler was we cast a very wide net. Kepler stared at a patch of 150,000 stars for 4 years without blinking. That was the secret of its success. If we want to discover more transiting planets, that is absolutely the way to do it. This is the best way to learn about the statistics of exoplanets, including small planets. Unfortunately, the transit requires such a particular configuration that if we want to know about worlds that are habitable worlds, that are near our own sun, 99.5% of Earth-like planets don't even transit. So this is a great way to learn about planets and their properties, not a great way to find the nearest Earth.
I think we'll take 2 more questions.
Thank you. I was just wondering, how difficult is it for you to track these planets given the fact that our Earth is rotating, moving throughout the solar system, and the solar system is moving throughout the galaxy?
Yeah, great question. What was your name?
My name is Doug.
Doug, yeah. So we have to account for the motion of Earth, including Earth's rotation and orbit around the sun, and subtract those out. The method of doing so is what we call a barycentric correction. If I ever make a pop band, that's what I'm going to call it.
Thanks. My name's Kevin, and just a question for you as you're getting ready to do this whole next stage. Do you have a candidate for the closest habitable world that you, putting all the different things you're you're putting together that you would say, oh man, I really hope it's this one?
Oh, such a good question. What was your name? Kevin. All right. So in the first video, there's a brief highlight of the nearest star system, the Alpha Centauri system. It's a triple system, 3 stars. If you've either read the 3-body problem or watched the TV show, I think it's on Apple TV, or is it Netflix? I forget. Anyway, that's a science fiction story about a world in this nearest star system. And some of my colleagues who use the Doppler effect have actually discovered 2 planets around the M dwarf, the lowest mass star in that system. It's not at all like in the science fiction version where the planet's getting chaotically kicked around. It's actually in a very stable orbit. Actually, both of the planets are in very stable orbits. The reason why I say my colleagues is this particular star, Alpha Centauri, is only visible in the southern hemisphere. We cannot see it from Hawaii.
Thank you, Dr. Weiss, and thank you all for coming out today.